Okay, so you may remember what we discussed yesterday. Let's continue from where we stopped. So this wonderful blockbuster of 2008. Let me remind you what the phase diagram is. So these are materials which are magnetic when not doped, still magnetic metals. You dope by electron holes or changing one nuclide by the other. In all cases, you get superconductivity. If you look at electronic structure at zoo, and you will see it, but we first started with the very, very simple model. And this simple model just had one whole Fermi surface near gamma point in the middle. We take two-dimensional systems because Fermi surfaces to a larger extent are cylindrical. So we took one two-dimensional whole Fermi surface in the middle and one electron Fermi surface in the corner, and ask a simple question: how can I get superconductivity in this situation if interactions are repulsive? And we play the same game as we played with cuprates with doped graphene. We said there are two interactions. One is small momentum transfer interaction is within pocket. Another is large momentum transfer interaction between pockets. Both are repulsive. But if we solve for the pairing, these are two coupling constants that we get. And condition is that for superconductivity, we need this coupling constant to be negative, means attractive, right? Think about Hubbard interaction. If U is positive, it's repulsive. If U is negative, it's attractive. So this is what we need. Obviously, we need this guy to be larger than this one. And we know that if we start with equal interactions, Kohn-Latinger effect will give you attraction, but we never start with equal interactions. We start with some interaction screened by high energy fermions, but it's still Q-dependent interaction in general. And of course, the one at small momentum transfer is generally larger than the one at large momentum transfer. So we have repulsion not only in ordinary S-wave channel, which is not surprising, but also in this channel. And we know that if there is attraction in this channel, we get what's called S plus minus superconductivity. So now we need to think a little bit deeper. And we say, look, for superconductivity is a low energy phenomenon. So we need energy smaller than Fermi energy. When we talk about interactions, we generally talk about interactions somewhat at the scale of bandwidths. There is a vague notion what the scale is, because of course we already include some screening from high energy fermions. But given that in nuclides this scale Fermi energy is at maximum 100 MeV, and in number of systems, including iron selenium, it's 10 times smaller. So it's a level of 1 MeV. A level of 10 MeV. That's 100 MeV. And in iron selenium, it's 10 MeV. And this scale is still maybe electron volt, not necessarily 3, 4. But still, there is a huge window. And then the question is, we need interaction here in this region. This is the story about interaction at this level. So how they flow, how they change when we integrate, what we do physically. We want to integrate out high energy fermions. We want to see how interaction is affected when we zoom at the system in energy space and look only at low energy part. Well, Kohn-Latinger effect, it's nothing but the first step in this process, because it tells you how these two interactions change when we include renormalization from particle-hole channel somewhere from this energy. So we prepare interaction at this scale by integrating out fermions with energies in this window. And this gives you U plus U squared, et cetera, et cetera. So again, if we start with repulsive interaction, we get some correction, but we cannot change sign by adding small correction. So we need definitely to go beyond this simple stage of adding U squared term and see maybe we can do better. And there is one thing that you all know. Yes, we can do better. We can do better if somehow our perturbation theory contains logarithm, which means strange thing, but we know how to sum up this term. So we know that if this coupling gets multiplied by logarithm of the running energy, then there is a standard procedure how to sum up infinite series of terms with leading logarithms. An example that everyone knows is a BCS theory of superconductivity. In BCS theory of superconductivity, when you look at the interaction, suppose we have some pairing interaction, just even not two scale, not two interaction, just one. Suppose we have just some pairing interaction. What we do in BCS theory? We start renormalizing this interaction and see how it changes as a function of temperature. And then there is a whole series of terms, Bayer interactions, then first normalization, the particle-particle channel, second one, third one, and we know what the final formula is. It's G divided by 1 plus G times log. So if G is negative, means attractive, we get superconducting instability when the total interaction blows up. It's another way to say that when temperature goes down, there is a growing attraction between fermions. At some point, fermions form bound state and then become, in BCS theory, immediately superconduct. I can equivalently, and this is the reason why I show you this graph, I can equivalently formulate the same problem in a slightly different way. I can say, let's consider interaction, running interaction at some energy scale E, and integrate over all energies between W and E. Then, summing up of logarithms is equivalent to writing and solving this differential equation. dg over d log of energy is equal to minus g squared. You solve this equation. It's trivial to solve this differential equation, and you get exactly the same result. In fact, it takes a little bit of efforts to prove that the equation is exactly like this, but you see from the result that you solve it, you get exactly the same, with the only difference that I replace temperature by running energy, but you understand energy and temperature are cousins in some sense, right? You will see differential equation later. So I just wanted to show you that this is equivalent to summing up logarithmical terms. Now, what we need to do is to find a way how to renormalize interaction between relatively high energy, where the interaction is a bare one, to the new one, which includes all effect of intermediate fermions. And when we look at this, we look at two channels, and here I have to be careful with you. We look first at particle-particle channel, the one that I showed you a minute ago in the BCS problem. But now we don't have Cooper logarithm. Why? Because we are above Fermi energy. We don't linearize near the Fermi surface. So we now deal with fermions with parabolic dispersion generally, and we are outside of standard regime of BCS theory. We are preparing interaction for BCS theory. We are asking the question, what is the interaction on the scale of Fermi energy? And you may say, okay, then it's a totally different problem. In some sense, yes. But on the other hand, if we're on 2 dimensions, and you allow me, just for sake of the argument, to use parabolic dispersion, k squared over 2m, then you know integral over d to k is the same, up to constant of course, as the integral over dispersion, right? K dk is d equal to d over k squared over 2, right? So we effectively get the same result as in Cooper problem. Namely, when we calculate particle-particle bubble, we integrate over frequency, we integrate over dispersion, reading it as integral d to k, and what we had out of these 2 green functions, we had 1 over omega squared plus epsilon squared. This give you log. In BCS problem, I would write numerator as kf dk, which means same as differential of k minus kf, and at the same time linearize dispersion near the Fermi level. So I'll get the same result by different reason. Only notice one thing, that standard question, why it's not working all the time. This is specific to 2 dimensions. If I would be in 3 dimensions, I would write square root of epsilon d epsilon. I put square root of epsilon here. I will get no logarithm, right? So this is logarithm specific to 2 dimensions. This is what essentially gives pairing interaction and bound state of 2 particles in 2 dimensions. Yes, please.
You saw the specific to parabolic dispersion?
As specific, well, yes, k squared dispersion. Yeah, right, right. If you have, but look, Fermi surfaces are small. So you generally expect the dispersion to be parabolic, right? There's no linear term of the dispersion. It's not Dirac problem. Yeah. Okay, but this is one thing. It's one channel. And then we know, yes, there are logarithms there, so we expect to write down some differential equation and find out how couplings change. What about other channel? And here we find a problem specific to iron pnictides. Remember, there are two dispersions. There is hole dispersion here, there is electron dispersion here. One goes down, one goes up. There is a momentum difference between two Fermi surfaces. Let's call this capital Q. Let me calculate particle hole bubble, but at momentum capital Q. And then I'll get up to overall sign exactly the same stuff. Why? Because now frequencies of these two guys are the same, of course, omega and omega, but dispersions are opposite. And in fact, this log is always associated with the word nesting. It's wrong. It's not nesting. I can take this dispersion with a mass which is 1,000 times larger than this mass. I'll still get log with some other coefficient. So all that matters is that one dispersion goes down, one goes up, and both are parabolic. Then you get logarithm instantly. So we have logarithms in particle-hole channel. We have logarithm in particle-particle channel. This is a wonderful situation because then we need to sum up leading terms in these two channels. It's a little bit messy, but we know what's going on physically. The two channels talk to each other. And then all renormalizations has to be calculated self-consistently in all channels. And basically what we have to do, we have to go beyond what we did so far. So far we introduced interactions in a particle-particle channel. Remember there was interaction G1 and G2. Solid and dashed line here just represent fermions from either hole pocket or from electron pocket. These are interaction within a given pocket. This is interaction between two pockets. I take two fermions from one pocket, transform into two fermions from the other pocket. By the way, quickly just to wake up a little bit. Why can we do it? Why can we write this interaction? What about momentum conservation? It works, right? Why? These two momenta are close to zero, for example. Each of this momentum is close to pi, right? So this is Umklapp process. Momentum is conserved up to 2 pi, right? If electron pocket was not at pi, I would not be able to write this, right? Okay, so we do it. But we also have to include interactions which normally operate in a particle-hole channel because they also logarithmically flow and they talk to these two interactions. So I introduced two other interactions. Which one? This is density-density interaction. Density in one pocket talks to density in the other pocket. And this is what's called exchange interaction. I take one fermion from one pocket, convert into fermion from other pocket, and do the same otherwise on a different side of the interaction. So that's really exchange between these two. You can rewrite this interaction in terms of Hubbard interaction, Hund interaction. It's completely equivalent language of writing the interactions. If I take these guys separately, this is what gives me pairing. If I take these guys separately, this is what gives me spin density wave instability. Yes, please.
So here in the square lattice, you mentioned that it is because you are at 0 and pi. But how about the honeycomb lattice yesterday? So that was because
Then you look carefully and you find out that again, this momentum is 1/2 of brilliance zone of reciprocal lattice vector.
Okay, it is always
Yes.
because
Yes.
there was another thing you mentioned that like Hubbard model couples all possible momenta. It's not related to that.
Hubbard model couples.
So the point like, so it's a point like interaction in space.
Yeah.
So then
Let's separate two things. This is a momentum conservation. Another thing is how interaction depends on momentum.
Right.
These are two completely different things.
oh, this is
This is just a question that I can write Umklapp processes.
Okay.
This has nothing to do with how interaction actually depends on momentum.
Okay.
Yeah.
Do you also need to consider the intra-pocket for the best for this part?
Well, wait a second. Intra or inter? Intra is this one.
Intra, but in particle in the particle channel.
Well, take this. It's the same interaction. Within one pocket, that's all you can write. There is nothing else you can write. Right? There's only one interaction within the pocket. Right? You kill two fermions, you create two other fermions. So this interaction G1 can be treated in a particle hole, in any channel you want. Right? Okay, so we have this. What's Konlatinger physics? You take this guy and see how they renormalize interaction. To first order, how they renormalize pairing interactions. This is what's going on. Now, I will not show you how to derive this. These are differential equation equivalent to summing up all possible logarithms in all channels. And you see it's called Parkia renormalization group. Why Parkia? Because there are logarithms, if you like, if you visualize. Suppose you write particle-particle channel as horizontal. Two particles are interacting like this. You write particle-hole channel as vertical. There is one incoming fermion, one outgoing fermion, and you write particle-hole bubbles like vertical line. Parquet means like you do flooring. You sum up a little bit horizontally, a little bit vertically, a little bit horizontally, a little bit vertically. That's why it's called Parkia, because you have logarithms in both channels. And long story short, this is result of summation of all logarithms. It actually doesn't take too much time to derive this equation, and people in Una's group here derived pretty much the same equation in different contexts. I just want to show you one thing, that where is the physics? If I neglect for a second communication between particle-particle and particle-hole channel, meaning out of this equation I take these guys, G1, G2, and this is G1, you see? This only particle-particle. This guy talks to G3 and G4, which are particle-hole interaction. Let me, for a second, neglect this. Let me write down equation, assuming that there is nothing in the particle-hole channel. I only look at particle-particle channel. I'll show you that the result is the same as we had before. These are two equations for pairing couplings without any renormalization from particle-hole channel. I can trivially solve this set of two differential equations. I obtain solutions, and you see what's going on. When G1 is larger than G2, these are Bayer values, you see that the running interaction only goes down, right? It never changes sign, it remains repulsive, and it goes down with decreasing energy. This guy, of course, also goes down with decreasing energy. So what's going on? Pairing interaction gets smaller and smaller and remains repulsive. This is the result what happens when you have repulsive interaction. Interaction just gets smaller, and this is sometimes what is called in high energy zero charge problem. Good, so we don't have anything. This is what we had before, that if you have repulsive interactions, there is no superconductivity. So this equation is nothing but a reflection of this statement. I just rewrote BCS problem in a different way. But we have the full set. So the question is what happens when the full set is solved. And then you find funny problem. This basically is the central result of the first. I want to finish this very quickly and move to the next stage. So this is what's going on. You see, remember, there was a good guy and there was a bad guy. This was a bad guy, G1, the one that was against any pairing. And this was a good guy, G2. That was in favor of S plus minus. If I previously remember, if I neglected G3 and G4, both went down. Now you see one guy actually goes up, another keeps going down. And so there is a scale when the system self-generates attraction. It's really funny phenomenon. You start with repulsive interaction, and at some point, the system changes sign by accumulating contribution from higher energies. The system changes sign of the pairing interaction. Where is Konlatinger physics? Konlatinger physics is here, if I can show it. A little bit small corrections to these two terms. So they come a little bit closer to each other, but they're still far away from each other. What is all this story? We go well beyond Konlatinger by summing up in a rigorous way, by summing up logarithmical corrections. We work in a situation when coupling times logarithm can be of order of 1, but coupling itself is small. So in this respect, the theory is a rigorous one. And the outcome, as you see, is that at some point, it's below certain energy, system generates attraction in S plus minus channel, as we expected for the Hubbard model right away. But now we just have a way to see it. But in doing this, we reach two goals. First of all, We can ask the question, why this happens? Well, because there is a push of good guy. Good guy is being pushed up by the interaction in the particle-Hall channel. And this interaction is called, if you look carefully at the equations, this interaction is called G3, and this is the one which favors spin density wave order. So in some sense, what I'm describing to you is an intelligent way to say that somehow pairing is mediated by spin fluctuations. Because as the system tends to develop spin density wave order, it also pushes up interactions that favors S plus minus superconductivity. And you clearly see this from the equations. What you don't see in a standard spin fluctuation theory is based on just, let's assume that interaction is already attractive, is the feedback effect. That growing superconducting fluctuations also affect magnetic fluctuations. And this has some consequences that I probably mention later on. I'll actually try to mention this if I have time.
So, Andrey,
yeah.
Whenever I try to communicate, this line of work to experimentalists or people who are, uninitiated with RG, I can go through the calculation and I see the negative sign show up, I see things diverge. The calculation does all the right thing, but I had a lot of trouble. I just haven't yet found a good way to communicate this in a more intuitive way, to somebody who's not initiated with RG. Do you have a way to talk about this?
In some sense, let me go back, maybe I can put it this way. I need to go back a little bit. Maybe I can go this way. It's enough. I just want to have this picture. In some sense, what we also are saying is a simple thing. We are saying that, look, the system has repulsive interaction. Raise your hand who knows what instability immediately appears in a system with repulsive interaction. SDW, right, SDW. SDW, Stoner instability in the simple metals occurs for repulsive interaction, right? So repulsion is good for SDW, repulsion is bad for superconductivity. Repulsion, if you look at the interaction and you ask what kind of SDW the system favors. The system favors SDW, sorry, I'll put one more thing. Which SDW can be with small momenta within this pocket or with large momenta between these pockets, meaning that I form either antiferromagnetism or I form ferromagnetism, right? Remember, the interaction between this pocket, particle-Hall interaction, is increased logarithmically. Interaction within this pocket is not increased by any means. So you expect that repulsive interaction will favor antiferromagnetism, right? Now, generally, if the system favors magnetism, this means that interaction between pockets grows substantially, right? Agree? Interaction between pockets is this guy. This is the interaction between pockets. This is the interaction that participate in magnetism. This is the interaction which participates in superconductivity. So you expect that when the system develops magnetism, this interaction should grow.
As a function of? As a function of?
As a function, when I progressively integrate out fermions, when I look at the system from larger and larger scales, and so look at smaller and smaller energies, or if you want, what to say, I look at the system at progressively lower temperatures, which also means that I progressively integrate out high energy contributions. So all I'm saying is that this interaction is participating in two processes. It gives rise to spin density wave, contribute to spin density wave. It favors S plus minus superconductivity. So not surprisingly that by coming closer to spin density wave instability, the system also favors this kind of interaction. The same result happens in RPA. RG goes beyond RPA in saying that when superconducting fluctuations develop, what they do is a feedback to magnetic fluctuations, how they all talk to each other. But the basic process is this one.
Then as far as the superconducting instability is concerned, I can just do RPA to get the roughly right answer?
Yes, you can. I think this is still better because RPA is uncontrollable, this is controllable. What you cannot do in RPA is find out that superconductivity occurs and no magnetism occurs. Because in RPA, magnetism is just put in, right? Here, all feedbacks are already included. Okay, with this, moves on, and very quickly, we have two competing instabilities. Now, we have one that is magnetism, we have another one which is S plus minus. You may ask what actually the system eventually prefer. So far, all we know is that magnetic interaction was attractive from the beginning, superconducting interaction was repulsive here. This is the effect we just described. It changes sign, it becomes attractive. For this particular simple model, we always have a situation when magnetism wins if we have zero doping. So these two lines don't cross. If you are at finite doping, eventually magnetism is stopped because basically of the difference between chemical potential of hole and electrons. But superconducting interaction, once it becomes attractive, it keeps going attractive. I mean, that superconductivity occurs whenever we have firm surface. And eventually superconductivity wins. But there are more interesting situations, and hopefully, I started later, so I have a little bit more time. So hopefully we'll come to a point when I show you more interesting pictures. Okay, so we are done with minimal model. The message from minimal model is that even if you start with repulsive interaction, and you allow me to sum up logarithms in two channels, you will get effectively attraction in a superconducting channel. That's the message. Now we start doing real physics. We ask a question, what minimal model misses? And it captures some physics, definitely, but it also misses some physics. So let's see what the full story is. First of all, superconductivity, I said S plus minus superconductivity. Is it the only option for this wonderful system? The answer will be no. There's more than one option. Magnetism. We said pi magnetism between hole and electron pockets. Is it the full story? The answer is no, it's not a full story. There is a much more complex story for magnetism. And finally, within one hole, one electron pocket, we even cannot address the issue about what is the interesting pneumatic order, which is seen here, the one that breaks C4 rotational symmetry, and the one that Seamus Davis was talking about yesterday. We just cannot do it because we just don't have any means. We have complete symmetry in X and Y. So let me say a few words about materials, and then we move on. Materials. So all iron pnictides are essentially layered materials, and the basic units is made of iron and pnictide or chalcogen, chalcogen are located either above or below iron plane. And if I take view from above, this is how it looks. Red are iron and say yellow are arsenic, but dashed and solid means that it is either above plane or below plane. And this causes immediately some confusion because theorists like me like simple things. So we all like to work in iron-only zone. And in iron-only zone, this is your elementary cell. It contains basically 1 iron per unit cell. But this square is not equal to this square because of position of pnictogen. So the actual unit cell is this one. It contains 2 iron per unit cell. So theorists like to work in 1 iron unit cell because it's much easier. Some experiments, magnetic experiments, are done in 1 iron unit cell. Why? Because spins are on iron. But photoemission experiments are done in 2 iron unit cell because this is the correct one. So the correct one is the one that has 2 iron in unit cell. And so you see 2 different types of Fermi surfaces. Just keep in mind that some Fermi surfaces are drawn in 1 iron unit cell. Some experiments, some data are drawn in 2 iron unit cell. You will see it in a minute. So if you look at this, you can say, I don't want to work on this field. This is band theory calculations of electronic spectrum, and this is a total zoo, right? But you look at this and find, wow, zoo in a level of what? From -6 electron volt to essentially +2 electron volts. So it's a huge energy scale, a lot of energy bands. But then you zoom into, this is just 5 iron zone without, I just take 1 iron representation and obtain 5 iron zones. And then I zoom into low energy part. And when I saw low energy, I'm not meaning 10 MeV. I'm meaning about basically 300-400 MeV, this region. And then within this range, you find out that in fact there is only 3 orbitals that contribute. This is the same as you heard yesterday during Seamus Davis' lecture. 3 orbitals are xz, yz, and xy. And this is orbital composition of Fermi surfaces. You see there is more than 1 and 1, of course. What happens, this is 1 iron unit cell, sometimes called 1 iron brilliant zone, sometimes called unfolded brilliant zone. So what you have in this zone? You have 2 hole pockets at gamma point, have possibly another hole pocket at pi point, and you have 2 electron pockets. One is located close to 0 pi, another is pi 0. Composition of these 2 pockets is xz, yz orbital. Composition of this pocket is xy/xz orbital. Composition of this pocket as xy/yz orbital. This is purely xy. So 3 orbitals, and they all contribute to Fermi surfaces. And you see, except for this one, which is mono-orbital Fermi surface, these are all multi-orbital Fermi surfaces. So means that if I go now to physics, when I write quadratic part of the Hamiltonian as simply epsilon k ck dagger ck, all information about orbitals will be in the interactions. Interaction will become angular dependent. This is something we didn't have in the minimal model. Now, you take this, that's the picture that I show. These pictures you see more as a sort of experimental pictures. This picture and these pictures are identical pictures. Only what I did, I folded. I said because of arsenic, I need to go to a different brilliant zone. And so what I do, I take this guy and move it to 0. I take these 2 guys and move together and declare the point where they move as a new pi point. So this, you probably can see it, although they're hardly distinguishable because they're very circular here. There are 2 Fermi surfaces here, 1 red, 1 yellow. These are these 2 guys. You probably see this guy right in the middle, right? There are 2 cylinders. These are these 2 guys. And 1 gas stuff in the middle is this one. This one is sometimes cylindrical. In lithium iron arsenic is cylindrical. But in many other materials it's just small sphere, in fact. It's not a cylinder. But these are details. We don't need to go into all details. So I just want to use this picture and these pictures are the same pictures. Where the fact that actual brilliant zone is folded brilliant zone matters. It matters when basically you need to include physical process of hopping of iron atoms through arsenic. Then you find out that there is what's called hybridization, that in fact you allow in your Hamiltonian in 1 iron zone processes with momentum transfer pi. And these processes exist. If you keep them, then obviously what you need is to go to 2 iron zone, and then what you get as simple dispersions in this kind of dispersions get what's called hybridized. You take another piece of this, which will be from another brilliant zone, and then merge them together. If there is no hybridization, they're just identical. If there is hybridization, they are not identical. And in particular, what it means is that these 2 electron pockets will split into 1 inner and 1 outer electron pocket. These are details. We don't need to go into all this. Okay.
In the folded zone, shouldn't the 3 orbital characters all show up now?
Sorry?
The HM has only XY.
Yes.
In the folded zone, in the physical system, they are not in 2 different.
That's what I said. You
points,
take
so
this point and move it here.
But
It's this one.
But then shouldn't the orbital content around us, given Fermi surface, involve all three orbitals?
There is a special for, in general, yes, but this is a special. If you look at the dispersion close to M point, you see basically color on these lines evolve percentage of.
Yeah, but I'm just wondering whether that's not a artifact of unphysically working the one iron zone.
No.
It is not.
The answer is this. All of them, of course, are composite of all three orbitals. The question about percentage of composition. If you look at this M point, this is your M pocket. It's this one, this whole pocket. And you see that other bands are few hundred MeV apart. You calculate percentages, you immediately forget about it.
Maybe another way to ask this is if you just actually do the calculation in the 2 iron zone, the DFT in the 2 iron zone, when you see the 3 pockets, is there one that only has XY character?
Yes. The answer is yes. Because in fact, the difference between 1 iron and 2 iron zone is this. You take these 2 guys and merge them into these pockets, and they can hybridize. These 2 guys also hybridize, but this one just simply transferred. Okay, now let's take this and discuss new features. And there are some of them. There are new features related to number of pockets. Previously we had 1 and 1. This was, of course, simplification. As we said, there are 2 or 3 whole pockets, and what's important, there are 2 symmetry-related electron pockets. These 2 guys are symmetry-related. If I have 1 here, then without any order in the system, by C4 symmetry, I must have 1 here. These 2 are just related by rotation by 90 degrees. And orbital content. As I said, we need to take into account that now we have orbitals, so interactions are angular dependent. And once we have angular dependent interaction, we can think about instabilities in non-S wave channels. For example, we can think about superconducting and Pomeranchuk instabilities in D wave channel. So very quickly, let's first look at spin density wave order. Remember, in a simple model, it was simple. It was antiferromagnetism with momentum pi. At that point, we even didn't talk about folded versus unfolded zone. You look at experiment, and yes, there is antiferromagnetism with momentum pi, but in the folded zone. If you look back into unfolded zone, iron only, unfolded, read for yourself, iron only zone, I forget about arsenic. In iron only zone, this is what's called stripe magnetism. When you have antiferromagnetism along one direction, but ferromagnetism along other direction. And it's pretty well established order. Well, it's called 0 pi or pi 0, because 0 means ferromagnetism along one direction, pi means antiferromagnetism along other direction. Which one? The system chooses. And then you look at basically the actual Fermi surfaces we have. I forget about this one, just let's do it simple way. There are 2 pockets here, there are 2 electron pockets here, and you say, yeah, of course, this is what I really mean by saying magnetism. Because what I had in mind is magnetism between electron and hole pockets. And of course, now I know electron pockets are here, not here. So this is where I expect magnetism. So there are 2 choices for this, either with this momentum or with this momentum. As a result, there are potentially 2 magnetic order parameters, one involving this pair, another involving this pair, right? And generally, we can ask a question which we could not ask in a minimal model. Which order the system wants? Does it want the order when both order parameters develop? Or it wants order in which only one order parameter develops? The system breaks symmetry between y direction and x direction. And there are choices. Oops, I need to put all of this, yeah, interestingly. There are situations where single order parameter develops. What you do? You need to derive Ginzburg-Landau model for 2 order parameters and then figure out whether both develops or only one of them develops. And the answer from theory is that both possibilities exist. And it can be 1 order parameter, which immediately give you stripe order, because each of this order parameter give you magnetism with momentum either 0 pi or pi 0, which is stripe. or both develop simultaneously, in which case you get, there's a fancy name for this, spin vortex crystal and charged spin density wave. But it basically means that both order parameters develop. Why there are two options? Because they are vectors. When both are developed, they can develop either perpendicular to each other or parallel to each other. This is perpendicular, this is parallel. You ask experiments. First of all, you ask theory. What theory tells you? It tells you that there is a stripe, but there is a possibility for one of these order parameters. Experimentalists tell you, yeah, I tried, I don't know how to do it on my laptop. What we need is to flip this figure, because this figure actually is, this is hole doping, so we go this way. So just flip this figure in your head. So this order is exactly the same as this one. So, yes, there.
2 minutes.
Oh, no, a little bit more.
Oh.
I started later.
Yeah, but not by that much.
Wow. Okay.
3 minutes.
Okay. Okay, very quickly. Then I have only to name the most interesting problem. So let's very quickly, in 1 minute, go over superconductivity. Superconductivity by itself is a very interesting question, but it will bring us to a lot of details. So first of all, what matters? Number of pockets and orbital content both matter. Why? Because, first of all, look at this structure. The easiest is to say, let's do the same as we did before, plus on hole pockets, minus on electron pockets. This will be simple plus minus superconductivity, meaning that this interaction is the dominant one. Well, we need to include the fact that we have orbital content, and we have also interaction between these two pockets, which we didn't have before. So to make long story short, two things. First, interaction become angle dependent because of orbital content. And once interaction become angle dependent, gaps become angle dependent. And as a result, if angle dependence is substantial, you may have something that you normally don't have in minimal model. Gap may have accidental nodes. And it was a substantial story for iron pnictides to look for accidental nodes. What I mean by accidental nodes? For example, you look at gap on electron pockets. Previously we had as just delta with one particular sign. Now by symmetry you can add these terms, which will different sign between two electron pockets. Despite cosine 2 theta, this is S-wave gap, because it changes sign, angle-dependent piece changes sign when I rotate by 90 degrees. And yes, in many calculations and in experiments, in fact, the nodes have been seen on electron pockets, and these are accidental nodes. They are not related by symmetry. They're just because interactions are angle-dependent. So you may say it's detail, but this is detail that, of course, affected experimental data, and therefore it was very important for interpretation of experiments. But there is more here. As I said, once you have pairing interactions, which are angle-dependent, you may ask a question, is S plus minus the only option? And the answer is no. D-wave becomes another option. So there is a whole story about possible D-wave pairing in iron pnictides. And there is one simple reason for D-wave pairing. If you take these electron pockets and suppose momentarily that this is a dominant repulsive interaction between electron pockets, you want to have plus minus between electron pockets, right? With the risk of taking 30 seconds of my time. If you have plus minus between electron pockets, what's the pairing symmetry? Always do this. Put your finger in the center and then rotate by 90 degrees. Your gap changes sign, right? You go from one electron pocket to the other. If gap changes sign when you rotate by 90 degrees, the gap symmetry is D wave, right? So this would be D wave. So this and angular dependence of the interaction forced a lot of discussions about possible D wave. And so there are systems for which there are still claims that this is D wave, they are D wave superconductors. And taking one last minute, pneumatic order. This is where orbital content and also number of electrons, but mostly orbital content matters. So pneumatic order generally is a very interesting phenomenon. It's a situation, Una, you will stop me, you just say stop and I will stop. interesting phenomenon where generally in many systems close to magnetic instability, you have another phase, which is non-magnetic, but it breaks C4 rotational symmetry. And in this wonderful compound called iron selenium, this phase exists in a wide range of temperatures without any magnetic order. And you see this from various experiments. You see structural distortion. A becomes not equal to B, means the system really becomes orthorhombic instead of tetragonal, spontaneously below a particular temperature. You see that there is orbital distortion, namely that Fermi pockets no longer preserve C4 symmetry. They become elliptical, and therefore they are more elongated along one direction than along other direction. And you see it also in magnetism, that susceptibility along x direction becomes not equal to susceptibility along y direction, and this is clearly captured by NMR. So structural distortion, there is orbital selective Fermi surface distortion, and there is also anisotropy of spin susceptibilities. They all are consequence of breaking C4 symmetry down to C2. So you break symmetry by rotation by 90 degrees and only leave symmetry between x minus x, inversion symmetry, and y and minus y. And of course, when we have 1, 2, 3 reflection of the order, the question is who is in the driver's seat, which physically means susceptibility in one channel diverges on its own and of course forces two other channels to do the same. And to make long story short, it's really a long story because there are a number of experiments. There is a very large number of evidence that this guy is not in a driver's seat. I'll just list you can read different experiments which all say the same. No, it doesn't look that structural distortion is the reason for this effect. And all theories say great, 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 because it means that this electronic instability. It's not something that lattice imposes of us, it's what lattice reacts to. And then two scenarios, very quickly. There are two dominant scenarios for pneumaticity. One scenario is very simple. It says that magnetism is the core. And scenario goes this way. Look at this magnetic order with momentum 0 pi or pi 0 in one iron zone. What symmetries this order break? It obviously breaks O3 spin rotational symmetry by just imposing magnetic order. But it also breaks symmetry between x and y direction by saying it's stripe along x or stripe along y, pi 0 or 0 pi. So we break two symmetries. This order breaks two symmetry. One is continuous O3, one is discrete Z2. In a mean field theory, you just get this order at one particular temperature, which means you break two symmetries at the same point. But the question that many people asked, can it be that you impose fluctuations and two transitions split? And the answer is yes, of course. We can split two transitions. One is discrete symmetry breaking, another is continuous symmetry breaking. How to see it? Well, it was done long ago, in fact. The answer is this one. Take two-dimensional systems. You cannot break continuous symmetry in 2 dimensions at finite temperature, but you can break discrete symmetry in 2 dimensions at finite temperature, right? Ising model has a finite temperature transition. Heisenberg model has 0 temperature transition. As a result, if you are in quasi-2-dimensional system, you do expect the two transitions to be separated. So this is scenario that before the system becomes magnetic. It has what's called vestigial spin-nematic order. Namely, it first breaks discrete symmetry and starts separating between x direction and y direction, in some sense preparing for a stripe phase that will follow. And then at lower temperature, it becomes magnetically ordered. Everything looks great, and there was a lot of calculations. I was involved, a number of other people were involved. There is only one problem with this. It's not a problem with this. You never can get wide range of separation between two transitions. They were always pretty close to each other. And we look at experiments and say, yeah, that's precisely what's going on. This is pneumatic transition, this magnetic transition. They're pretty close to each other. This is pneumatic transition, if you can see it, this magnetic transition. Yeah, they're pretty close to each other and they follow each other. So in this case, I would say, yeah, it's probably this scenario is real story. But there is this wonderful material, iron selenium. Simplest possible iron-based superconductor, just iron and selenium, nothing in between. And you see this is iron selenium. And you see pneumatic transition happens here at 85 Kelvin. You go down, there is no magnetism. Superconductivity emergence at lower temperatures, but no magnetism. And when people saw this, there was immediate question, can it be that at least in this system, the reasoning is something different? And of course, let me mention works done here, our works, the works done by Igor Mazin and Roser Valenti. Basic message is this: yes, there are magnetic fluctuations in iron selenium, definitely. You look at neutron scattering, there is measurable chi double prime peaked at some fixed energy, so you do see magnetic fluctuations. However, you look at what happens with magnetic fluctuations around pneumatic transition temperature, around 90 Kelvin, and you don't see any appreciable temperature dependence. While if you have this vestigial magnetic order stuff, you expect susceptibility to react. So you expect some temperature dependence of susceptibility to appear. And although it's not a final word, but it's possible that magnetic fluctuations are not responsible for pneumaticity in iron selenium, which let's take it as a working hypothesis for really the last minute. And then you can ask a question, if not magnetic fluctuations, then what? Well, there is another possibility. What about Pomeranchuk instability? What about that the system develops spontaneous orbital order? Meaning spontaneously density of an xz orbital becomes different from the density of yz orbital. It's a density wave order, charge density wave order, with zero momentum, so it's Pomeranchuk, and because it changes sign under rotation by 90 degrees, from x direction to y direction, this is d wave. And this brings me to the very last part. What if we redo Rg that I started this talk with, but now include all orbital content of interactions? So what I want to do is this. I want to put on a start, this means we start Rg, with all these contenders, superconductivity in S and D channels, spin density wave. And I put two orbital channels, S plus minus and D. And I now want to do the same I did before, but of course in a much more complicated way, including all three orbitals or 5 bands, which means 44 coupling constants. But it's doable. It's still doable even with 44 coupling constants. The question is, who is this guy, right? Who will finish first? I'll remind you that when we put only 2 guys on the starting line, we get this story that repulsion was converted into attraction, and these 2 guys compete, and magnetic fluctuation force superconducting fluctuation to change sign and become attractive. What happens if I put all of them at the start? Then we get one more element of the story, that not only superconducting fluctuations, but also orbital fluctuations change sign due to tendency towards magnetism and become attractive. So now there are 2 channels that are forced by magnetism to change sign and become attractive. And the question, who wins out of them? And what they combine do to magnetism? And here is the result. You run all this wonderful Rg for many, many coupling constants, and we have a number of ways to do this, but here is the result. So starting process. Magnetism is the driving seat. Blue is the magnetism, largest susceptibility. Second comes superconducting. Third comes pneumatic susceptibility. You run Rg, and you see what's going on. Pneumatic susceptibility eventually becomes number 1 instability in the problem, which is very interesting. So it wins over other cells, and it has higher exponent in susceptibility. There is a caveat. I promise you I will tell you about this. Magnetism doesn't develop. So when this guy and this guy become attractive, they combine kill the source. So they force magnetism not to develop. So if you do it like this, you find, say, aha, this is my orbital order. Great. The system develops orbital order instead of superconductivity. I'm good with iron selenium, but not good with other systems. And then you ask a final question. So is it the only answer? No. Why? Remember, Rg works in a finite range of energies between roughly bandwidth and Fermi energy. In iron selenium, this is really small scale. So we can expect that this all runs within this range, and we get some divergences before we reach AF. If it's not the case, if we have larger Fermi energy, then Rg stops here, and essentially we have to cut it here. So then the guy who was number 1 will eventually win. So Parkia Rg only runs between bandwidth and Fermi energy. When I reach Fermi energy, I stop there, and I need to do then. I know physically what happens at lower energies. Channels stop talking to each other, which means I can now run RPA in every channel independently. They no longer talk to each other. This means that this is the situation when magnetism wins, superconductivity is number 2, and orbital order doesn't develop at all. And this is basically, oops, why it's not going? Interesting. This means, oops, yes. This means I have to stop, but you see its conclusions. So I'm done. Yeah. So basically, here is my message. That if you do all this, I try to go into circle with you. But if you finally do this stuff, you find out that pnictides are wonderful systems in which Rg helps you, and also logics help you. And I foresee 2 possibilities. One in which essentially the system starts as showing largest tendency towards magnetism, but as all channels talk to each other, eventually the largest tendency becomes tendency to orbital order, following tendency to superconductivity. So the system first develops Pomeranchuk instability and then superconducting order. This is one option coming from this picture. Or there is another option that magnetism develops, superconductivity tends to come closer, and I may even put line here, may even overshoot it, but pneumatic fluctuations are very, very weak. So I think that some materials are here, some iron selenium is here, but what is nice is that within the same approach, we can describe both as just 2 limits. And I guess this is pretty much what I wanted to tell you about iron pnictides and chalcogenides. Thanks. At least I'm not that much off in terms of time.
No, you're actually that's so bad. Maybe 1 or 2 questions, if there are questions. Yes.
So in your approach, do you also need to consider the flow of self-energy to consider the reshape of the Fermi surface, or even include damping?
Good question. Within Rg, strictly speaking, self-energy is not included. And the reason self-energy is not included is because it also gives you logarithms, but with higher powers of the coupling constant. So strictly speaking, playing the game, I include coupling times logarithm, but I don't include coupling square times logarithm. Then you don't include self-energy. There is Rg, proposed Rg that includes self-energy, but then you need to soften the rules a little bit. It's a good question how self-energy generally affects all these conclusions. Probably not that much for iron pnictides, because there is no evidence from photoemission that self-energy is singular. I mean that self-energy extracted from photoemission show pretty much normal properties up to energies of few tenths of MeV. But for the cuprates, it's really an important question. Yeah.
So what about the single layer iron selenide where there is no pocket in the Jones center?
2 parts of the story. One is, given how much time I have, I had to cut all this part. I had 6 transparencies on this, which I didn't show at all. So there are 2 possibilities. There are theories being included, but actually Igor Matin started as this. Basically saying that there are 2 choices, and one is D-wave, trivial D-wave between 2 electron pockets, which probably inconsistent with experiment. Another is more fancy possibilities. I mentioned hybridization. It splits electron pockets into inner one and outer one. And you can get a state which will be plus minus between these splitted pockets, which is more likely candidate. This is what Igor Matin called other S plus minus. But whether it can give large TC, nobody really knows. And there are 2 examples. One is single layer iron selenium. Another is potassium iron 2, selenium 2. There's more accurately 2, 4, 5 materials. They have also only electron pockets. They don't have substrates there, bulk materials. They have TC of 40 Kelvin. So whether they are in the same ball game or not, I don't know. But these are another story which is not full end. So nobody calculated TC with prefactors, so we just don't know the answers. And very last word for iron selenium, I'm neutral about whether it's iron selenium monolayer. I'm neutral about whether it's intrinsic or it's induced by substrate. I just don't have good opinion about this.
But because you don't have what enters to that bubble is interpocket. And when you don't have that, you can't really do RG to
Absolutely, absolutely. It's a totally different story.
So this whole approach
Whole approach is not applicable. Yes, whole approach is not. All you can do is to solve essentially mean field or RPA equations. Yeah, it's much less accurate games than this one.
All right, on that note, let's go for coffee and wake up.
Okay.